Good morning, everyone. Welcome on this fourth day of the summer school, the last day with lectures, unfortunately, or maybe fortunately, depending on your state of mind at this point. So in this morning session, we're going to talk about what imprecise probabilities can do in the setting of uncertain processes. And I will be teaching this lecture jointly with Michael. So let's think about what is an uncertain process, sometimes also called a stochastic process. What I'm going to assume is we're interested in a sum system, and the system has a state. We know all the possible values that the state can take, and we collect this in the state space, which I denote by this curly X. And now this state changes over time, and I'm going to denote an arbitrary time index by lowercase t, and then I'm going to collect all of the time indices that I'm interested in this blackboard T. Right? And the crucial part now is that we are uncertain about how this system changes over time. Okay, so we have an uncertain state at every time index t, which I denote by capital X sub t. So this is the abstract framework of uncertain processes. But perhaps it helps to make this a bit more concrete. So just like Matthias, I'm interested in wave heights here. This is a system, it's a very nice shoreline, and I'm interested in the wave height here. I'm not a meteorologist, I don't have a very good meteorological model, so I'm uncertain about how the wave height will evolve over time. Anyone recognize this coast? It is coast near Llanes in Asturias, near the Bifones del Pria, and I'm interested in the wave height there because there's a very cool natural phenomenon that happens when the waves are sufficiently high. Good, that's one example. So it's wave heights, but not for windmills, but just for tourist reasons. Another example can be the queue in front of your favorite ice cream cart or ice cream shop. I'm uncertain about when people will arrive, how long they will take to take their order, and how long it will take until they get serviced. So if I'm interested in finding the optimal point in time where I need to go to the ice cream shop, I need to model this as an uncertain process. And then finally, one more example. An internet router usually has a buffer, and then the occupancy rate of this buffer, the number of packets of data traffic that are in the buffer, this is also an uncertain process because I never know when someone will want to access something on the internet. Okay? So the previous two examples are probably easiest to model in continuous time, or to think about in continuous time. But this one, the clock speed of a buffer, of an internet router is always discrete, so this makes sense to think about this in discrete time. And this is also the setting that I'm going to consider in this third part of the lecture. I'm going to keep things as simple as possible, so I'm going to assume that there's only a finite possible of state. Right? The buffer size is finite, there's only a finite number of possibilities, and I'm also going to assume discrete time. So I'm going to index the time by the natural numbers, 1, 2, 3, and so on. So this is arguably the easiest setting to consider uncertain processes, and then later Michael will go on to more difficult state spaces and continuous time. Okay, so now we have one uncertain state for every time point, so we can represent this visually or graphically by putting our random variables or our uncertain variables on the number line. So now we have one uncertain state for every time point, and then just a reminder, we know that each of these states assumes values in the state space, which will be finite now, and I'm always going to denote states by lowercase x, y, and so on until z. So this is the setting. It is a graphical representation, but it is not the most useful graphical representation in this setting. One that is a bit more useful is the representation as a situation tree. So this is a tree where every node represents a situation. And what is a situation? It is a specification of the states in the first n time points. So we construct this tree starting in a root node with the empty situation. We know nothing about the system. And then this root node has one child for every state, right? So this node y represents the fact that the state in time 1 will be y. And then each of these states, again, has one child for every state. So for example, the situation xy means that at time 1, I had state 1, x, and at time 2, I had state y. Okay, so this is a situation tree. And if I go further and further down the tree, this means that at each state, each next time point, I learn the next state. So this is a representation of the behavior of the system. But I want to be able to represent my uncertainty about the system, right? So I need to add something to the situation tree, and that is I need to add probabilities. Right, so what I'm going to do now is I'm going to attach a local probability mass function to every situation. In other ways, another way that you can think about this, I'm going to attach probabilities to each of these arcs, each of the edges that go out of a situation, and then these need to sum up to 1, because we want a probability mass function, right? So this will be numbers between 0 and 1 that sum to 1, or in other words, a probability mass function attached to the situation. So just that we're all on the same page, I'm going to denote the local probability mass function in the initial state by pi subscript 1, and this models my beliefs about the state in time 1. Okay, and then in every situation, I will have a local probability mass function which I will denote by q subscript the situation, and then this models my beliefs about the state in the next time point, so about the state in time n plus 1, given that I've seen the states x1 at time 1 and so on until the state xn in time n. So this is the information that I need to provide to end up with a model of my uncertainty about the system. And I can combine this information and use whatever theorem you want to end up with a global model, which is technically a probability measure, but it doesn't really matter for our purposes. Just know that if I combine this local information, I can get a global model of my uncertainty. Okay, somewhat clear? Good. So let's look at this global model a bit clearer. I'm going to fix some situation, x1 to xn, and I'm interested in the probability of this situation. So I know I'm interested in the probability of the state at time 1 being x1, state in time 2 being x2, and so on all the way to time n, the state being equal to xn. And I want to express this using the information that I supplied, right? Using the local probability mass functions. Any ideas how I can do this? We basically saw it yesterday in Alessandro's lecture. Bayes rule, yes. So we're going to apply Bayes rule once first. So if I move this part of the equation to this side of the equality, I have Bayes rule, right? This is the multiplicative way of Bayes rule. And this I should recognize, this second term, because this is the one I supplied, right? This is the local probability mass function in the situation x1 to xn minus 1, evaluated in xn. So I can replace this one, this term I know. Now what I'm left with is this one, and I can do exactly the same trick again, and again, and again, and again, and again. And so how do you call this, Alessandro? Iterative something? Sorry? Chain rule, yes, the chain rule. And so eventually I will then end up with a lot of products here of things that I know, and then one conditional probability that I know as well, and then this is the initial model that I had as well. So I can replace this, and I see that if I want a probability of some situation, I can find this as a product of things that I know, things that I supplied to the model. Maybe this isn't the easiest way to think about this, but it's easy to think about this when you look at the situation tree. So what this formula tells me is that I need to go from the initial state all the way to the situation. So if I'm interested in, for example, the probability of the situation xy, I start in the root node, and I want to go towards the situation that I'm interested in. And every time I take an edge, I take a look at the probability of that edge, and then I multiply the probabilities that I see along the way. So in this case, I would have to multiply the initial probability mass function evaluated in x, and then this local probability mass function evaluated in, what was it? Y. What is it? Okay? So that's one way to think about this, is to go forwards in the tree or climb up the tree. But it will be more convenient in later stages to think about this as descending down the tree. So if I'm interested in this situation, zy, the same thing I can do. I can start here and then climb down the tree and multiply all the probabilities that I pass to get the probability of that situation. Yeah, so we can either think forwards or backwards in time, and it will always help to think backwards in this case. Is this clear? Good. Okay, but we're interested in making decisions using our model, and then we're not only interested in probabilities, but usually these come in the form of expectations of certain variables. Okay, there's a lot to be said about variables in processes, but I'm always going to assume that we're interested in finitary variables. And with a finitary variable, I mean one that I can represent as a function of some of the state in the first n time points. Right, so this can be, if I'm thinking about the example of the internet router, this can be the maximal size of the buffer in the next 10 clock times, or in the next 10 time points. There's also other type of variables, and usually these are the ones that are more interesting, and these are non-finitary, so variables that I cannot express as a function of the first n time points. One example would be the time until the buffer of the router is empty. This I can never write as a function of the first n states. Okay, so but for the sake of simplicity, I'm only going to deal with finitary variables. And then you can do some other things if you're interested to get to non-finitary ones. But okay, let's assume we have this finitary variable, so we're interested in the expectation of function of the first n states. Then we use the well-known formula. We've seen this plenty of times, right? The formula for the expectation of a function. So we take a sum over all situations of length n, and then we take the product of a function value in the situation and the probability of this situation. And now we know what the probability of this situation is. So we can again think graphically about this formula. Let's say I'm interested in a process that has two states, A and B. And I'm interested in some function of the first three states of this process. What I'm going to do is I'm going to stop my tree after I've reached situations of length 3. And I'm going to write down the function value next to each situation of length 3. And now what my formula says is I need to sum over all situations and take the function value with this product. So I start in a situation, I take the function value, and I go down the tree, and I multiply all the probabilities that I pass along the way. And then I do this for every situation, and I sum up all these values, and I get the expectation of the function that I'm interested in. Seems quite inefficient, right? So luckily, there's another way to do this. And one way to realize that this is possible is to rewrite this sum. So I'm going to split up this sum into n sums, one for every time point. Right, and I'm going to isolate all the terms that don't depend on the summation variable. I'm going to take out of the summation all of the terms, that don't depend on the summation variable. And then I get this expression. Is this more or less clear? Does this help me? Okay, someone who's not familiar with Markov chains, does this help me? What is the last term? I'm taking the sum over all states of a product of a mass function evaluated in a state and some function of this state, right? So I can think of this as rewrite this. Okay, so we're interested in this thing, and I want to write this as the expectation with respect to this probability mass function. Right? So this should be a function of xn, but it's a function of x1 to xn. Okay, so we're fixing x1 to n minus 1, and then trying to write this as a function of xn only. So I want to write this as the expectation with respect to this local probability mass function of some function of x1 to n minus 1. Okay, let's call this h subscript x1 to n minus 1. What should be the expression for this function? It's a real valued function on the state space. And it maps xn to... Sorry? Yes, first x1 to n minus 1, and then xn as well, right? Or perhaps it's easier to write this as x1 to xn minus 1 and xn, where xn here is the variable. Right? So we're fixing the first n minus 1 components in this argument. This we're taking fixed. And then we're only looking at the function in the last component. So this gives us a function of the state, of a state tuple of length 1. Okay, and now I'm hoping I'm not confusing you, but I'm going to use a slightly different notation. So I'm going to write this slightly differently. Okay, so here I fixed 1 to n minus 1, but I'm taking a summation over all possible combinations of x1 to n minus 1. So I'm going to write this as follows, as a function g of, no, sorry, I'm confusing myself. I'm going to write this as f x1 to n minus 1 with a bullet. Right, so this notation means I'm looking at the function f, which usually takes n tuples. I'm going to fix the first n minus 1 components, and I'm going to look at this as a function on the last component. Right, so that's what I did here. I'm taking the expectation with respect to this local probability mass function of this function where I'm fixing the first n minus 1 components, and I'm looking at this as a function on the last component only. Right, and then just to make writing this a bit easier, I'm going to construct a function g that takes n minus tuples of length n minus 1 and maps this to the expectation with respect to the corresponding local probability mass function of this function. So this term here becomes g of x1 to n minus 1, and we see that we get the same expression as we had before. So now we've turned an expectation of the function of the first n states to an expectation of the first n minus 1 states. If this is all a bit weird, I'm just using the law of iterated expectation or the tower property, if this rings a bell. So I'm using this to get from a function from the first n states to a function of the first n minus 1 states, and I'm doing this by using all of the local probability mass functions in the last situations. But as always, it helps to think about this graphically. So first we had this situation, whoop, I need to go back here, yeah. First we had this situation, right, where we have a tree of length 3, and then a function value next to every situation of length 3, and now I'm going to write this as something that only depends on the tuples of length 2. So in each of these situations, I'm taking an expectation, right, with respect to this local probability mass function of the function that is here, where it's only the last component that I'm interested in. I'm fixing the first two. And this brings me to this situation. So everywhere I've taken the expectation with respect to the local probability mass function of the function where I fixed the first two components, and I'm looking at the last one, and I'm only allowing me to vary the last one. And I call this function g, right? So this is taking a function f of the first 3 states to a function g of the first 2 states. Why does this help me? Or why is this useful? Because I can do the same thing again, right? But now for a function of the first 2 states to get to a function of the first state. So I had a function of the first 2 states. I'm going to take the local expectation everywhere, and I'm now and I'm looking at the expectation of a function in the first state, and this one I know, it's just the expectation with respect to the first initial probability mass function here. So that's an iterative way to compute the expectation. So rather than fixing every situation and going down the tree, I'm always going up one level in the tree. Right? It's a different way of thinking about it, but we're doing the same. And it will be important later on. Okay, so this seems to work, although it's all a bit unwieldy. And that is because for every situation, we need to specify a local probability mass function. And these situations, they're countably infinite. Right? So if I want to specify a model of this form, I need to specify a countably infinite amount of local probability mass functions, which is difficult. So something needs to give if we want to use this in practice. Right? If we want to have this as a practical model, we need to make some simplifying assumptions. And again, this brings us back to Alessandro's lecture. We're going to make the Markov assumption. And this is the actual root of the name Markov assumption. Because Markov was the first to do this in this setting. So I'm going to, again, look at my beliefs about the state in time n+1, given the information that I have about the states in the first n time points. And now I'm going to assume that if I know the state in time point n, so in the current time point, all the information that I know about the states before is irrelevant to my beliefs about the states in the next time point. Right? So this is the Markov assumption. It's exactly the same as we saw in Bayesian networks. So it's assuming that if I know the state in time n, my beliefs about the state in time n+1 do not matter or do not depend on the states in times 1 to n-1. So this is the Markov assumption, and I'm going to add one more simplifying assumption. But maybe first I should mention that what have we done now? We've turned our uncertain process into something that we saw yesterday, into a Bayesian network, which I can draw easily. It starts in x1, then it goes to x2, then it goes to x3, and so on ad infinitum, right? Because my beliefs, if I know x2, my beliefs about x3 are independent of x1. This is exactly what we saw in Bayesian networks. And now we see that this forms a chain of states. Good. So I'm not only assuming the Markov assumption, but I'm also going to assume time homogeneity. And this means that the actual location of my current time point doesn't matter. In every time point, I will always think the same about the next state. So in another way, you can think about this as an absence of seasonal effects. Or an absence of time effects. Probably if you're thinking about a router, there's times where the internet traffic will be more busy and times where the internet traffic will be less busy. But now we're assuming there's no influence of time, at least not on my beliefs. This is perhaps a bit difficult to understand, but it's always easier to think about this graphically. So I have exactly the same thing. I have a probability tree, still have an initial probability mass function. In the first layer, I still have a local probability mass function, but now in the second layer, I'm reusing these local probability mass functions based on the last state that I observed. Right? So here in ZY, I'm using the same local probability mass function as the state Y. And similarly here, if this last state would be a Y, I would use the same local probability mass functions. So over time, my beliefs about the next state don't change. This is time homogeneity. And so again, we can use this local information to end up with a global model, and this is what I'll call a Markov chain. And we've indeed succeeded in our goal. We've really simplified this model, because now we need to specify one initial probability mass function, and then for every state, and there's only a finite number of states, one local probability mass function. And these ones I will call a transition probability mass function, because they tell me how I transition from a state in time n to a state in time n+1. Okay, so that's really nice. Although we've made a very, very, very strong simplifying assumption, right? We've made this very strong irrelevance assumption in the form of the Markov assumption, and then this time homogeneity assumption as well, which is not always justified. But usually if you want to do something in practice with this model, you really need to make this assumption, just to keep the computations tractable. Okay, so let's see what these assumptions can do for us, how they simplify our lives, or how they make our lives less complicated. So I'm again returning to the situation where I have two states, A and B, and now I'm interested in the expectation of a function that only depends on the state in time tree. Okay? And by now you know what to do. If you want to compute this expectation, we do one step of this recursive scheme, right? So in every situation of length 2, we're going to compute the expectation of this function with respect to this local probability mass function. And one important thing to note here is that in AB and in BB, we will use the same local probability mass function, right? Because B is the last state that I observed, and I don't care for the first state because it doesn't change my beliefs due to the Markov assumption. So what we'll get is this. And now see that in AA and BA, we get the same value. And in AB and BB, we get the same value. So twice we get a function on the state space again. We have two possible values. And for this, I'm going to add a little bit of notation, because always going on to this function g is a bit annoying. I'm going to add some notation. And this notation will be the transition operator. What is this transition operator? It takes a function, a real function on the state space, and it gives back a real function on the state space. And the image of a real function f on the state space is this. This I find false, so it's, again, a real function on the state space, and it maps a state x to the expectation of this function f that I'm applying my transition operator to with respect to the local model or the transition probability mass function for x, right? So one thing that we should note is that for any x, we have that the expectation with respect to qx of f is equal to the image of f under my transition operator evaluated in x. Okay, so it's just a different way of writing these equations, or these expectations, sorry. Now in my example, this means that this function here is the image of f under my transition operator, and this function here is again the image of f under my transition operator. Okay, so I know now that the expectation of f of x3 is equal to the expectation of the image of f under my transition operator evaluated in x2. Okay, so I have again something of the form, the expectation of some function of the state in time point 2. Now I can do the same step again, and I will get here, I should have added a step in between. So let's see. We'll do it here. We're taking the expectation in this situation b, so it's with respect to the local model in b of this function. So here we will get the expectation with respect to qb of the function t of f, and this we know is t of f evaluated in b, right? So that's how we get to this, and t of f I will write as the square of f, or applying t twice to f and evaluating in a. And now I've written a function, so the expectation of the function f of x3 as the expectation of some function in x1 of x1, and so I just need to apply the the initial probability mass function to get the end result. So what I see now is that I'm interested in the expectation of a function of x3. I can find this as the expectation with respect to the initial probability mass function of the image of this function f under two applications of my transition operator, or one less than I have here. Okay, and I know this is only the binary state space, but I'm assuming that you believe me if I say that in general, we find this equation here. So for a function of a state in time n, I can find this as the expectation with respect to my initial probability mass function of this function, which is the image of f under n-1 applications of my transition operator. Okay, so it's a very concise way of writing this down, which was, in essence, always doing backwards recursion. And we can use this transition operator to write something else concisely as well. So we're looking at, we had this function before, right? If we're interested in the function of the first n states, then I can go and rewrite this as a function, as the expectation of some function of the first n-1 states using this function. But now this resembles something that we saw before, right? We can write this as how can I use this? How can I rewrite this using the transition operator? What matters is the final state here, so it will be something of the transition operator. Evaluated in xn-1. And what should be the argument? The same function, right? The function that is here. So it's f x1 to n-1 with the bullets. So this is a function on the state space, right? We fixed x1 to n-1. Then we applied the transition operator to this function, and we evaluated in xn-1. Right, so that's what I've written here. And this means that we can rewrite this equation as follows, where I'm using the transition operator. So this thing here, well, actually this thing here, is a function of the first n-1 states. That's the important thing. And I can use my transition operator to turn a function of the first n states into a function of the first n-1 states. It doesn't really matter if you don't completely understand. Just remember the form of this equation, because we'll need it later on. For now, let's focus on this one. This will be easier to grasp. And I've written this in a perhaps not in the most clear way. So this is a function. This is an operator that takes functions to functions. And this is, again, an operator that takes functions to real values. But we can think about this completely in terms of matrices and vectors. So I'm going to fix some ordering of my state space, and then look at the canonical basis, where this ix1 is the function that has 1 on x1 and 0 everywhere else, and this is a function that has 1 on xm and 0 everywhere else, right? And then with respect to this basis, my transition operator has a matrix representation. This is linear algebra. And this representation is pretty easy. On the first row, I just put the components of the transition probability mass function of the first state. And then so on until I reach the last row. And here I just put all the components of the transition probability mass function of the mth state. So that's how I fill this matrix, and we will usually call this the transition matrix. So perhaps if you're used to working with Markov chains, if you saw Markov chains, usually this is the thing people start from, a transition matrix. And it's comparable to, what did you call it? The conditional probability tables in Bayesian networks. Okay, why is this useful? It's because now I can rewrite this formula using this matrix. So if I'm applying the transition operator to a function that is the same as applying the matrix representation of this transition operator to the column vector of the function values, right? So that's what's written here. I can think of T of f in my basis as and this will be the transition. Okay, now it's becoming difficult. The transition matrix times the column vector representation of my function. Yes? Because here I'm only interested in the function of the state at time n. I'm not interested in the state of 1 to n. I'm only interested in the state at time n. So this is a function on the state space, not on the tuples of length n. Okay? Okay, so now I see how this, okay, I've done this for one application, but you get the same for n applications. This will be this. So if I'm interested in, or n minus 1. If I'm interested in applying the transition operator to a function, I can also just multiply the matrix representation, or the transition matrix, with the row vector corresponding to my function. And then to take expectations, I can do the same, right? An expectation with respect to a probability mass function is the same as multiplying the row vector of the probability mass function with the column vector of my function. So that's how I get to this formula. Yes? The definition of the matrix? Of the basis. We're just using the canonical basis to make things easy for us. Okay, let's see how much you've understood from this by looking at an exercise. Yes? Sorry, you want to ask why this is in 1? Sorry? Why only n? Right. Yeah, okay, an example of a function that only depends on one time point is the people that will be in line in the ice cream shop at 4 p.m. later today. Right? Or the number of packets that will be in the buffer of the internet router 4 minutes from now. This is an example of a function that only depends on the state in a single time point. And these are also the ones that are most basic and the easiest to study. Okay, but this is the formula that we need, and we'll need it in this exercise. Okay, there's multiple ways to solve it, but the easiest one is to use the formula before. So again, I'm going to assume a binary state space with states A and B. For the initial probability mass function, I'm going to assume that we put all mass on state A, which is as saying that I'm absolutely sure we'll start in state A. Then I need to also specify the two transition probability mass functions, right? For A, I'm going to assume that with mass A, alpha, I stay in A, and with mass 1 minus alpha, I go to B. And for B, I'm going to assume that with mass beta, or with probability beta, I'm staying in B, and with probability 1 minus beta, I'm going to A. And what I want to know from you is determine this expectation. So it's the indicator of B, the function that is 0 on A and 1 on B, of x3, and this is exactly the probability of x3 being equal to B. And in some sense, since we're assuming that we're starting in A, this is the probability that I start in A in time 1, and I will end up in B in time 3. Right, so these transition probability mass functions tell me in one step. Now I'm interested in what happens after 2 steps. And if you want to calculate this efficiently, you could use this formula. But let's see how you do. I'll give you a minute or two to try. Okay, has anyone managed to come up with an answer? Does anyone dare shout their answer? I think you have one product term missing there in the last. Oh no, are there silent parentheses there? Okay, could be. Could be. Okay, let's see. So what we want to use is this formula, right? For n equal to 3. So this means we need the second power of the transition matrix multiplied by the row vector of the indicator of B, and then with the column representation of our probability mass function. So that's this, okay, the second power of our transition matrix, the, I always forget the column vector of our indicator, and then the row vector of our masses. So we fill in what we know. This is the indicator of A, so it's 1 on A, 0 otherwise. For the transition matrix, we just fill in this row. We just fill in this as the first row, this as the second row, and then this is the column vector of the indicator of B with the 0 on A and 1 on B. And now we do the matrix calculations, and we should get this. Alpha times 1 minus alpha and beta times 1 minus alpha. Yes. Good. We can do a quick sanity check here. What are the possible ways that I can go from A to B in 2 time steps? It's to either go from A, stay in A, and go to B, which is alpha times 1 minus alpha. Or we can go from A to B and stay in B, and this is 1 minus alpha times beta. So that's how we can do a quick sanity check. Okay, the point of this exercise is not to torture you with matrix computations. It's just to make a point that if you have this transition matrix for a very large system, you can just plug this in a computer and let the computer do all of the hard work. And this expression will come up later in the presentation again. So we need this one. Okay, so that's a very short argument as to why Markov chains are a very useful model. They allow for efficient computations and so also for easy decision making. Of course, there was this one caveat. It was a very difficult, very hard, very strong simplifying assumption, right? The Markov assumption in time homogeneity. So whether or not this is justified is something that you should do on a case-by-case basis. But there's an implicit assumption in this model. What is the implicit assumption? Yes, that we know these probabilities exactly, right? We've assumed that I'm able to specify these probabilities, so that the expert who I'm trying to use, whose knowledge I'm trying to use to build a model, is able to specify these probabilities exactly. But there's no reason why this should be the case. Also, there's no reason why these should even be exact probabilities, right? But if you think about this in an elicitation type point of view, where I'm trying to learn this model from an expert, he's probably more willing to provide bounds on probabilities than provide exact values. So I'm going to ask myself, what if we do not know these local models exactly or precisely? Okay, what if I do not know them exactly? What can we do? Yeah? We could go immediately to upper and lower expectations, yes. That's a very possible route. But I'm going to assume that instead of knowing these probability mass functions exactly, I just know that they should belong to some set. I'm willing to say that I have some set of initial probability mass functions, and for every state, some set of transition probability mass functions, be it because someone specified bounds, or because I've learned these, and I have some kind of, it's not a confidence interval, but some kind of range of possible values. So what I'm going to assume is that I have sets of candidate or possible initial probability mass functions and sets of transition probability mass functions. And so in my tree, instead of everywhere having probability mass functions, I now have sets of probability mass functions. Okay, I'm going to denote a set of initial probability mass functions by capital Pi sub 1, and then these sets of transition probability mass functions by curly Q subscript the state that they belong to. So now this is the information that we have for our model, a set of initial probability mass functions, and for every state, a set of transition probability mass functions. But now, again, I want to go from these local assessments to a global model. So this is a form of extension. How do I do this? I know it's a bit of a difficult problem, so let's say we want to keep in, or we want to remain in the same language. We want to go from sets of local models to sets of global models, sets of probability trees, sets of Markov chains, sets of global models. Then I guess the easiest thing to do is just to look at all possible Markov chains that I can construct using this initial information. Right, so I'm going to construct a compatible Markov chain, and the way that I do this is I pick one of these initial probability mass functions, and then for every state, I'm going to choose one of the transition probability mass functions in this set. This gives me a Markov chain, and I'm going to do this for every possible combination that I can make. Right, so these I'm going to call the compatible Markov chains, the Markov chains that I construct in this way. I'm going to look at a set of all compatible Markov chains. This is the natural thing to do, I would say. If you think about this, it makes sense to do. So now we have a set of compatible Markov chains, not just a single one. We want to do inference, right? We want to compute the expectation of functions because we need them to make decisions or something like that. And so again, I'm only going to consider finitary variables. And now the upper expectation or the lower expectation, right? We have a set of models, so we don't have a single expectation, but a range. And I'm interested in tight lower and upper bounds on this range of possible values. So I'm going to consider upper expectations, but you can always consider lower expectations and take the infimum everywhere if this is more your cup of tea. But I will use upper expectations. So for the upper expectation of a function of the first n variables, this is just the supremum over all compatible Markov chains of the expectation of this function for this Markov chain, or the expectation of this variable. Right, makes sense. This goes back to Erik's lecture. And then a particular case that I will consider is where, again, we have a function of only the state at time n. Right? So I don't care about the first n minus 1 states. It's only a function on the state n. So we have the same formula. And this is the expression that we had for Markov chains. Right? OK. So that's in general. Let's look at this for an example. So we have exactly the same. Sorry, yeah. Yes, because every model that I'm considering is a Markov chain, right? It's a time homogeneous Markov chain. You use the same one, yeah. You pick one for every state, exactly. And this should be the same for every time point. Good point, yeah. Okay, so I have exactly the same setup as before. I'm again going to assume that I know that I start in A, right? So the set of initial probability mass functions is just a singleton that puts all mass on A. And then for the transition probability mass functions, I have exactly the same form as before. So mass alpha, for A, mass alpha on A, mass 1 minus alpha on B. And now alpha can range between 2.5 and 3.5. So we're going to do a numerical example. Same for the transition probability mass functions for B. We can range beta between 1/3 and 1/2. And what I want to know from you now is, what is the upper expectation of this, the indicator of B evaluated in X3? Or in other words, what is the upper expectation of finding ourselves in B at time tree. Let's see. I'll give you a couple of minutes to solve this. Okay, just a reminder, these are all the compatible Markov chains, right? This expectation we've already determined. This was alpha times 1 minus alpha plus 1 minus alpha times beta. And now we need to optimize this over all compatible Markov chains. Okay, so we've turned this question of determining an upper expectation in solving a quadratic optimization, a quadratic constraint optimization problem, right? We have constraints for alpha and beta, and we have a quadratic objective function. You can solve this any way you want. I did this lazily. I just looked at the plot in Python, and I can see that I reach a maximum for alpha, the lowest possible value, and beta, the highest possible value. And if I fill this in, I get... Whoa, that was a very big murmur. I get 27 over 50. Yes? Okay, well done. Well done. Okay, just a couple of remarks before the break. So this was okay. Yes? No, you can also go back, right? You can go from A to B, but also from B to A. But yes, in this case, you can do it that way, probably. Well, yes, it depends on the range of alpha, but it also really depends on your objective function. Yeah. So, okay, in this case, it might be obvious, but if you go to higher state spaces and more and functions of further time points, for example, it can get more involved. Good point. But the point I want to make is, okay, even for this simple case of two states and 2 time points away, we already have a quadratic objective function that we need to optimize over some constraints. So in general, I think you can see that this becomes a very difficult problem because we have quite a lot of parameters, right? In general, we have one probability mass function for every state and then one initial one. So we have, what is it, n plus 1 times n minus 1 parameters that have all some kind of bounds because they need to be in some set, and an objective function that really the only way to determine this objective function is to do this calculation, right? For every possible combination of parameters, I need to do this computation, and then I have an objective function that I'm trying to optimize. So optimizing this thing in general is quite difficult to do in an automated way. So it's hard. It's hard. But it can be done. And we'll see if we can do anything about this after the break. I hope that before the break I convinced you that computing upper expectations for the set of compatible Markov chains is hard, difficult, not what we want to do. And if I'm not convinced you, just believe me, please. So let's see if we can do about this. We have some initial data about the local probability mass functions, right? Sets that we can have them in. And then now we investigated the set of all compatible Markov chains. Right? But there's no real reason why I should restrict myself to Markov chains. Unless I really believe that the Markov property and the time homogeneity property, that they are valid, there's no real reason to restrict myself to them. So what I'm going to do now is I'm going to look at the set of all possible compatible probability trees, or all possible uncertain processes, or stochastic processes, where compatibility now means that the initial mass probability mass function still has to be in the set of initial probability mass functions. But now I need to require that in every situation, right, the local probability mass functions that says something about my beliefs about the state in the next time point, this should be in the relevant set of transition probability mass functions. And so for this, I look at the last state of the situation, and this is the transition probability mass function that I will use. The set of transition probability mass functions that I'll use. So now I've gone from the set of all compatible Markov chains to a much larger set of all compatible processes. So these need not satisfy the time homogeneity property nor the Markov property. Okay, so I've not only relaxed this requirement of precision for my local models, but also in this interpretation of the set of global models, I've also relaxed the assumption that they should be time homogeneous or Markov. So it's 2 birds in 1 stone now. I have both initial model relaxation and underlying independence assumption relaxation. Okay, so now we have a much larger set of compatible probabilities. This means that the upper expectation with respect to this set will be greater than the one with respect to the set of compatible Markov processes. The question now is, of course, The optimization problem that I need to do to compute upper expectations, is this more difficult, easier, the same? Who knows? You will know in a minute. So we're going to look at this with the same exercise as before. So again, we have the binary state space, the same data, the same bounds, and I'm asking for you to compute the upper expectation of this function of the state of time 3, or the upper probability, so you want, of going from A in time 1 to B in time 3. So, okay. I will help you a bit along the way, but first, maybe it helps to think about this yourself. So what we're trying to do is we're trying to determine the expectation of this function for all compatible Markov processes, all compatible processes, all compatible probability trees, and then optimize over these expectations. And in this case, a picture is worth more than 1,000 words. Okay, so this is an optimization over the set of all compatible processes, all compatible probability trees, and I'm optimizing over this expectation. So let's draw this, because we know computing this expectation for a generic probability tree is, we draw it and then we go back one level, right? So let's draw this again. We get this picture, right? We have a probability tree up to level 3. I've indicated the values of the indicator of B next to the situations of length 3. And now, okay, in general, I know I can choose a probability mass function everywhere, right? Independently of each other, I can choose a probability mass function. The only thing is they need to satisfy these constraints. Okay, and now there's some clever way in which you can do this optimization, but I'll let you think about this 2 more minutes before we see if someone has come up with the solution. Anyone has an idea how we can solve this computation or this optimization problem? Let's just assume that I've fixed all of these local probability mass functions for a moment. Then what I need to do to compute the expectation is do the backwards recursion, right? So first, in every situation of length 2, I'm going to compute the expectation of this function, 0, 1, with respect to this probability mass function. And then in the next level, in every situation A and B, I'm going to compute the expectation of the function that is now on these nodes and on these nodes. And then here, I'm going to compute the expectation on these nodes, of the function on these nodes with respect to this probability mass function. Okay, and now I know that I can choose these probability mass functions as long as they're in these sets. And my objective is to get eventually a value here that is as large as possible. So how do I need to choose these probability mass functions? If I've arrived at this point, it's easy, right? I'm choosing the mass function that assigns the most mass to A or B, depending on which one is greater. But I don't know what the value was here. So let's go up one layer. The function that I have here. This again will be the expectation with respect to some mass function of the function that is here. But I don't know what the value will be. So we need to go up one more. Some kind, yeah. So now here, I'm computing the expectation with respect to every mass function. In every situation of this function, with respect to this probability mass function, I can choose this freely. Now, if in the end, okay, I'm going to always go back one layer, and I want to find the highest possible value here. What do I need to choose in this situation as a probability mass function? The one that maximizes this one. Why? Can you give an argument why? It can be an intuitive one. So our objective is to find the highest possible value here. We can do that by maximizing this, but we can also maximize the function values here. Right? Here again, our objective is to find the highest possible values here. So we need to take an expectation. We can choose the probability mass function, but also the values. So we're always going to put mass on the function value that is the highest. So it is in our best interest to here find the highest possible function values. I have freedom to choose everywhere, right? But it's easiest to start at the back. Choose the one here in every node that maximizes. Right? So if the one that maximizes here is the one that goes to B as fast as possible, right? So I'm taking A lower on A, 1 minus A lower on B. And here I can do the same as well. I'm always going to try to get this value as high as possible, because I know in the end, it'll combine it all the time into some value. So everywhere here, I'm going to choose the highest value. And I can go back one layer, and this gives me these values. And now I'm going to do exactly the same, right? Here I'm going to choose the one that optimizes. Here I'm going to choose the one that optimizes. Then I have a value that is as high as possible. And I'm going to do the same here. And then we should find the end result. And I'll give you 2 more minutes to try and find that. Has anyone found the value yet? Okay, we'll just do it jointly because I need to speed up a bit. So okay, here we can choose this probability mass function, or we can choose the value of alpha, and we want to put the most mass on A, right? Because that's the highest value, so we're going to use alpha overline here, or the upper bound. And here, what we want to do is we choose beta such that we have the highest mass here, so we're going to use beta lower here and 1 minus beta lower here. That gives us this, and then now there's no choice here. There's only the indicator of A, so we need to take this value. So we find that the expectation that we're interested in, or the upper expectation that we're interested in, will be this expression. This is we recognize this, right? It's alpha times 1 minus alpha plus 1 minus alpha times beta, and this is equal to 28 over 50, if I haven't made a calculation mistake. 28 over 50. And before, when we optimized over the set of all Markov processes, we found 27 over 50. Right? So we see that in this case, the upper expectation with respect to the set of all compatible models is strictly larger than the upper expectation with respect to the set of Markov processes. So we know that it's a non-strict inequality in general, and this is an example where this inequality is strict. So we can do more. The reason why this is because before for the compatible Markov processes, we had the same expression, right? But there we couldn't choose alpha and beta independently, right? Here we can choose alpha. We could choose alpha independently here and here, and here and here. Oh no, not here and here. Here and here we can choose alpha independently, and here we can choose alpha and beta independently. While before we had to use the same value of alpha and beta everywhere. Right, so this allows us more leeway to get to a higher value. Good. Now this was a, yes. Oh yes, sorry. So this was for a particular example, but we can do this for any function f. And the way that we get to the upper expectation here is always, we're going to use backwards recursion. And in every node, we're going to choose the probability mass function that locally optimizes the expectation, right? And for this, I'm going to introduce some notation. So now, in the Markov case, we had the transition operator. Now I'm going to introduce an upper transition operator, which is again a map from the real functions on the state space to the real functions on the state space, and it maps a real function on the state space to this, again, a real function on the state space, but now, for every component x, it is mapped to the upper expectation with respect to the set of local probability transition mass functions for x. Okay, so before we had the expectation with respect to the local transition probability mass function. Now we have the upper expectation with respect to the set of transition mass functions. And this is an example of what is known as an upper transition operator or a sublinear transition operator, sublinear Markov kernel. It's any operator from the set of functions on the state space to the set of functions on the state space that satisfies these three properties, and these should look familiar because they are versions of the three coherence properties that we saw in Erik's lecture on the first day. Okay, so since it's defined as an upper expectation for every argument, it's easy to show that this upper transition operator satisfies these three properties, and then any operator that satisfies these three properties we'll call an upper transition operator. It's not really important for now, but it is for the project. So now, okay, what we're going to do backwards recursion. Everywhere we're going to choose the probability mass function that optimizes my local expectation. So what this means is that everywhere I'm going to get the function value that I can find by applying the upper transition operator. Okay, so now I've turned an upper expectation on triples to an upper expectation on a function on the doubles, right, on the two first state spaces, and I'm going to do exactly the same. I'm going to choose each time the transition probability mass function that maximizes, or Ergo, I'm going to apply my upper transition operator to the function that I had before. And now it's only left, it's an optimization over the initial models. And so basically, we get this formula. I know it's only in the binary state space, but you'll have to believe me that this also works for larger state spaces. So what we've shown is that just like we had in the precise Markov chains, we have this type of formula where it's an upper expectation with respect to the initial probability mass functions, and then my function f that I'm interested in, to which I apply my upper transition operator n-1 times. And so we see now that if we want to do this not on pen and paper, but in a computer, this is easy, right? I can start with a function f, and then I apply my upper transition operators n-1 times, and I just take an upper expectation, finally. So it's a much easier way of doing the optimization. I can do it in a backwards recursive manner. So if I can evaluate this upper transition operator easily, which usually is just a collection of linear programs, then I can easily do this computation. So it's a much easier optimization problem. We have a much larger set of compatible processes, but funnily enough, this gives us enough degrees of freedom to make the optimization problem easier, which I think is a really nice result. And then just for the sake of completeness, I will also mention that if you're interested in functions that depend on the first n states, you can do something similar as we had with precise Markov chains, where we can use backwards recursion every time to go to a function that depends from the state on the first n time points to one on the first n-1 time points, and so on and so on and so on. So there you do, again, backwards recursion in the tree, where now we use the upper transition operator rather than the transition operator. So this is a very weird way of writing the tower property for upper expectations, or the law of iterated upper expectation, if you want. Okay, so that was that. We saw two types of compatible Markov chains, sets of compatible processes. Optimization here is difficult. Optimization here seems to be nice, or computing upper expectation here seems to be nice. But then there's this blank void here that is not there for nothing. And that is because there's an extra type of process that we're considering. So one of you already hinted at this. There's no need for us to use, at every time point, the same set of transition probability mass functions. We could now use the inhomogeneous Markov chains, where we have the Markov assumption. So it is the last time point that determines the transition probability, but it can be different from time point to time point. So here, with situations of length 2, if the situation is zy, I'm using the same local model as if the situation would be xy, but not necessarily the same local model as where the situation would have been y. So I'm dropping the time homogeneity assumption. I'm allowing for seasonal effects. This is what we call the time inhomogeneous Markov chain. And then I can consider the set of all compatible time inhomogeneous Markov chains as well. All the Markov chains are included, and it is included in the set of all compatible Markov processes. If we think about this in terms of independence assumptions for Quidel sets, this is epistemic irrelevance, and this is complete independence. Just to tie it back to what Erik and Alessandro said. This one is often also called an imprecise Markov chain under, what is it, repetition independence that you call it? Yeah. Just to let you know that these terms exist. Okay, we have another set of models. This also means another set of upper expectations. What we are guaranteed is that they are in between the ones of the set of compatible Markov processes, chains, and the ones of all compatible processes. And now the big question is, how do we compute these upper expectations? So for the initial models, for functions of the initial state, they will all be the same because we have the same possible range of motions. You can do this, you can verify this yourself. Then, a bit of a challenging homework exercise, or if you want to do it formally, or if you want to do it just by an argument in trees, maybe this is quite not too difficult. Does this same formula hold for the set of imprecise Markov chains? Sorry, for the set of compatible time inhomogeneous Markov chains, as we had for the set of all compatible processes? This is one question that you can solve at home. And then this one is even more difficult. Can we also use this backwards recursion for functions that depend on the first n states? Okay, so this one is true. I guess you can easily check this. This one, maybe you already have an ID from the graphical proof that we used. So let's see. Who thinks this will not hold? Who thinks this will hold? Okay, I guess you can do this, try to do this at home. I can just say, draw the scheme and try to go over the proof again. And this one, I can tell you now, it doesn't hold. Find a counterexample, if you want to. Okay, I'm almost there. Just have one more thing to say. There's this one way of doing imprecise Markov chains, looking at a set of compatible processes, but this is not the only way. Instead of using these sets of local models, I could just start with the upper expectation with respect to this set, and then for every state, the upper expectation with respect to this set of transition probability mass functions. And I can try to use this information to extend them directly to a global model. One way is to use the game theoretic upper expectation. I don't have time to go into this. I just want to mention this because it's a very strong framework, allows you to prove very nice results. There's references at the ends of the slides, but this is the framework championed by Glenn Schaefer and Vladimir Vovk, and also by Gert and others in our group. So just to know, there's different ways of doing this extension. Another one is to start from, again, the upper expectation for the initial model, and then an upper transition operator, right? This is in one-to-one correspondence, if you want. And you can immediately extend this to an upper expectation on the set of finitary variables, or even larger, if you want. And this satisfies then the two expectations, or sorry, the two properties that we saw earlier. Just as an aside. And I think this will tie in nicely with the way that Michael will present his work. Now, before I hand the words over to Michael, I just want to say a couple of things about the project. So one thing that I haven't really touched upon is limit behavior of these chains. So if you have a Markov chain with a transition operator T, in some cases, this iterated application of T to F converges to a constant function. And when this happens, we call this transition operator or the Markov chain ergodic. Now, why is this relevant, that this converges to a constant function? Sorry? Well, okay, it's a nice mathematical result, but it's also nice practically, because what this does, right, is it gives us the expectation of some function f of xn. And if this becomes a constant function, then it doesn't really matter what my initial probability mass function is. I will always converge to this, the value of this constant function. Okay, so I know that for very large values of n, this will converge to some value, and this value is completely determined by the transition operator T. Now, there's necessary and sufficient conditions for this transition operator to be ergodic, and actually there's also very easy ways to find this constant value that don't require you to do the actual limit computation. Now, we have something similar in the imprecise case. So if you have an upper transition operator, you can again say that it's ergodic if, for any function f, the nth iterate of this upper transition operator eventually converges to a constant function. And this is relevant for the same case. In that case, it doesn't matter what our set of initial models is. The upper expectation of this function f of xn will always converge to the constant value of this function. So that's why you might be interested in this. Again, there are necessary and sufficient conditions for ergodicity, but in this project we will try not to look at these, try not to look at the literature, and try to rediscover these necessary or sufficient conditions ourselves. And these always have a very nice, or you can arrive at these conditions, I should say, in a very nice graphical way. So it seems to be a pretty abstract problem, but there's a very nice, concrete way of thinking about it. There's more information in the project description. And there's one more aside. You might think that there's an easy way to compute this constant value, but I know of none. So if you want a really challenging problem, you can also try to tackle that one. But that would be all. Thank you.